Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Ricardo López-Valdivia with us today. Hey, Ricardo.
Hi, Frank. I really appreciate this opportunity to talk about our more recent results. So thank you.
Well, thank you so much for agreeing to talk about your very lovely article, which we will get to in a little bit. It's awesome. It's very cool. Ricardo, where are you located at?
I'm in a small city here in Mexico called Ensenada. It's about 1 hour and a half from Tijuana. Probably most people know Tijuana than Ensenada. So here I'm part of the Astronomy Institute of the UNAM. So here is another campus. There is another campus in Mexico City. So we are really close here to the National Observatory. We are like 4 hours from that. So it's part of the duties of the Institute, just preserve and maintain the observatory too.
Very cool. And on a slightly different topic, I think Ensenada is a fairly popular surfing spot, if I remember right.
Yes. For me, it's a little bit strange. I had to be honest because it's the beach, but mostly beach in Mexico are really hot, and here it's cold. It's cold now. It's like I would say like a upper 50s Fahrenheit.
Oh, okay.
So it's cold.
Okay. Very cool. Very cool.
Yes.
Well, I'm in Phoenix, and it is February 13th, 2023 as we record this, and spring is starting to break in Phoenix. We're getting a little rain today, but the temperatures are moving up, and you can already kind of feel spring in the air a little bit. So
really?
Yeah, so it's coming. It's coming.
Yes.
Very cool. And Ricardo, what do you like to do for research?
Actually, I will say I like to, like a summary, I like stars. I like to work with stars. I start my research with stars like our sun, solar-like stars, solar twin stars, just trying to characterize and trying to understand the stars of this kind, just trying to looking for exoplanets. That was my field, how I get into the astronomy at all.
Cool.
After that, when I was just doing my PhD, so I was just learning more and more about stars, and I just love it to do the characterization of stars. So then I move a little bit to characterize a different stars, so a cooler stars. So I move from solar-like stars to stars like a K and M, so they're cooler stars.
Yep.
And also I just move from these stars well-behaved, like our sun, I will say well-behaved our sun, to the Joan stellar objects, Joan star, proto stars. They are not well-behaved, so they are different, but I like to do that and work with a spectra.
Awesome. Very nice. And that is going to bring us to this very awesome APJ article. It is open access, people. You can go get a copy for free. Go grab a copy. The IGRINS YSO Survey 3, stellar parameters of pre-main sequence stars in Ophiuchus and Upper Scorpius. And Ricardo, take us away.
Okay. Well, here, as Frank said, this is you see that number 3. So it's the third of this series. Is the IGRINS YSO survey. So this is just part of my job, or part of the research I did as a postdoc in the University of Texas. So here are some of my collaborators, some people that are involved on not just in this paper, but also in all the IGRINS. I don't know how to say it, all the IGRINS stuff, right? So
the program
is a really all the program, and since it's an awesome instrument, probably we'll see a little bit more in the observation. You will probably believe me that is an incredible instrument, and really I think there should be more like IGRINS in other telescopes, not just one around it.
Very
right?
good. Very good. Yes.
We will talk a little bit more in the paper, but it is really interesting. And the main goal of this paper was, you see the third. So the beginning, it was just try to understand young stars. So to try to study young stars from the spectra in the optical wavelengths is really complicated, because John stars are embedded in dust and gas clouds, and it's really complicated to see it in the optical wavelength, right? So
yes,
to try to work in this wavelength or with these objects is better to move to infrared. So
yes.
this is an instrument that works in the infrared, and that was the main idea. I mean, the main idea that we have, or at least the part I have, and it was interesting to me, it was try to understand how the parameters, the stellar parameters that we will see, was the stellar parameters, I mean, affect the evolution of the stars. So it's more or less that idea, and try to see this. It's not an easy task, and we will see why. So this is just the third part, because we start with something closer region and most studied region as Taurus. And Taurus stellar region, that was the first paper. Also, the second paper of this series was about the veiling. So this veiling is something really interesting and really complicated to take into account, but must to be include in your analysis. If not, you could have erroneous results. So that's another thing. And this is the third part, which we extend a little bit with this Ophiuchus and other Scorpion members as a smaller sample, and we just try to complete or complement the first part of the paper. So it's more or less the idea. The idea is try to see if we can differentiate, for example, class 2 and class 3. So more or less ball objects, they are different in terms of gravity, temperature, magnetic field, for example. So this is another thing, interesting thing about this work, is we introduce into the play the magnetic field effects. So most of the people just avoid this because it's really complicated. So it's easy to avoid it. And you know, you have some good approximation, but you need to, as we have better and better instruments, we are able to see it. And we need to improve our knowledge of the things. So
cool. Yep.
So here, more or less, the introduction is talking about the John stellar objects, which we know that, as the name says, is the first stage of the stars. They are just evolving. As we are working with spectra, we need to see lines, right? So there are different classes of John stellar objects. We focus more or less in class 2 and class 3. We will see, so we can see the stars. So we have this photospheric emission in the lines, and we can see it, and we can characterize the lines of the star. Cool. So basically, the nice thing about this thing is that we need, for example, the temperature and the gravity, and we can just compare this with the evolutionary models. And with that, we can just know about the masses, the ages of the different regions. So basically, that's the way we are obtaining the information about these two parameters. So basically, these atmospheric parameters that I call atmospheric parameter, which is temperature, gravity, rotational velocity, and also magnetic field that we include here. So those, for example, temperature and gravity permit us to obtain a fundamental parameters as mass and age, right?
Yes. Yes. So, yes.
Here is interesting. When as I told you before, I was working with main sequence stars, just solar-like stars. So when I just jump here to the IGRINS data, and I started to see the spectra, it looks different, right? It looks very different. And also, I just moved from the optical region to the infrared region. So it looks completely different. But it was really interesting just at this effect about the veiling, which is just a continuing emission that is being explained by different things, like the accretion, the emission of the inner gas ring, which is warm. So this veiling, the thing is doing is making the lines shallower. So all the lines are shallow, and if you don't take into account at the beginning, people just measure the temperature of gravity or the parameters, they will obtain erroneous results, because this decrease in the depth of the lines will mimic some of these effects, temperatures of gravity.
Oh, yeah.
So it is really complicated. So some of them, there's complication just lead to a group in UT and in Kasi in Korea just tried to do this. Dan Jaffe in UT tried to create this instrument, this amazing instrument, this emission gradient infrared spectrometer, which is called IGRINS. So it's I don't know, for me it's really interesting because it's a small instrument, it's really small, really compact, but have a lot of technology, I will say, behind it. It's really nice. It's using these immersion gratings so that you can just read more about the technical details. But the thing is that you can have smaller instruments. In this case, it's silicon, and you can obtain a resolution of 45,000. Mm-hmm. And you have the possibility of obtaining in a single exposure the H and K band.
Cool.
So it's really interesting. It's something that no other instrument can have. Most of the spectrographer, you can change the setup and move around and try to improve your resolution, or you just move around across the wavelength space. Here, you can, in single exposure, you have more or less the H and the K band, and also the median resolution is 45,000, which is a really good,
very nice,
high resolution.
Indeed.
Another thing with this instrument that for me was just blow my mind. It was designed to be in the McDonald Observatory, but it's so, I don't know the word to say, but versatile probably, that just change a little bit of things. It can just visit different telescopes, and it was visiting telescopes in Arizona. The Discovery Channel telescope now is Lowell Discovery Telescope. It was like if I'm not wrong, like 3 times there, 3 different periods of time, and then just move visit Gemini South in 2018, and then come back to some maintenance and come back to Gemini South. Right now it's in Gemini South. I understand that it's just in the last part on the last semester down there, and come back to Texas. It's really nice. This is really good instrument, and I have a lot of good science behind. This is just a part of the science that you can do. Yeah. But there is a bunch of things that you can do. Other people, collaborators there, and they're doing things on exoplanets. They're doing things with magnetic fields more in detail. So there's not just this. It's more about that. But this will be just some of a small survey just to prove it that is working, and it was working really good.
Yep, very nice.
So the idea is the resolution is good enough to obtain some results. So here the observation is something interesting, since the first light of this instrument was in 2014. In McDonald, it was just observing different people, just like ask for time. Just say, I have this project about this thing, about this young star. The main program of IGRINS in the beginning was just try to do this survey in YSOs. They started surveying Taurus region, Taurus Auriga Star Forming region. Then just try to move to Ophiuchus and Upper Scorpion, but from the north is a little bit hard to get it. So because it's a south, because the coordinates of these regions. So I started just trying to survey the sky with different projects. And here for this part, we just try to focus on the K and M stars. So we have observation, a lot of observation, and there is now actually available to the public all the observation from 2014, since the beginning, up to 2021. Cool. So anybody that wants to use this data, not just this data in the paper, but others, I just really encourage the people just to look for this thing is RISA, it's called RRISA, which I don't have it here side because it was not published at that time, but now it's published, and you can just download the paper, download the data and everything. If and
we will put a link to that in the description below the video.
Perfect. Thank you. Yeah, so from all this archive that we already have, you can imagine we have hundreds and hundreds of observation, and I will say thousands of different objects with different epochs of the observation and different goals. of course, scientific goals. So for this, I just try to look for the stars with K and M. I could in M5 because late types than M5 for me will be really difficult to see the lines. It is complicated because we will see the technique that I was using, or we were using, I should say we, because it's a teamwork, we were using is compare the observation with a theoretical counterpart. So the theoretical counterpart, there's not good enough in this temperature, not yet. We are not yet there.
Okay.
So we just focus in this kind of stars, K0 to M5, and we just do another cut, quality cut in the signal to noise around 70 in the K-band. So because this is the third paper of the series, in the first paper, we just make just all these kind of tests to see which is our limit. And our limit is around signal to noise 70. We obtain a reasonable work. So basically, this part of the observation is just how to say, there's those people that different techniques have to observe. I think is we can just pass to the different to the section number 3, which is the determination of the parameter. If we can jump to figure 1, I can just show how IGRINS spectra looks like, which you will see is just a small pair. This is just a really small pair. Remember that I have the H and the K band. So I will just try to, in a moment, just to explain why I focus to this small part, this for small part, but you can see here a typical spectrum. This is like a spectrum with a signal to noise, I will say really good, really nice, and you see how the different features that you see, sodium, titanium lines, calcium, and also molecule like a CO, they are really nice. So this is for me really nice, and just it's something that is really good. And you will see how I always interested in how these things change if I change the temperature, for example, or if I change the gravity, or the different things, right? So this the determination of the parameters is just basically using an MC technique, Monte Carlo chain, Markov chain. Sorry, I don't know. I just always
MC.
Make a mistake with that, with the MC, with this technique. So basically, we were doing try and error, just trying to see which of these region in the H band and the K band were better to reproduce to obtain the parameters. And this searching, or this thing is which is better, is because the models, right? It's not about the observation, it's about the models. We need to figure out which region is better in the models to try to reproduce the observation. So at the end, this is a series of theories, but previous to this, the first paper of this series, we were working on the determination of temperatures, just temperatures, for field stars. So this well-behaved stars. So I come back to the well-behaved stars, right? So we figure out there, and we will next we'll see that we took those stars into here, and we will see what's the result of this. So it's just basically we created a synthetic spectral library. We use this code called MOOC stocks. Probably people know about MOOC, which is this really nice code that was made by Chris Sneed, UT Texas.
The original MOOC,
to try to synthesize spectrum. So here, Casey Dean in 2013 just modified that model, that code, sorry, to introduce the effects of magnetic field. So now we are able to not just reproduce or not just synthesize a spectrum, but also just saying, hey, here is a magnetic field, a stellar magnetic field of this quantity, what's happening in the spectra, how is this affecting? So we already know from physics class and everything that there is the Zeeman effect, that in the presence of magnetic field, external magnetic field, you will have a split into the levels of energy. So this in the how to say transform to to the spectra, you will see a double line. So you will see how the line will start to split as the magnetic field increase.
Good.
So we had the available. MOOCs has a lot of assumptions, as many of the codes, if not everything, all the codes have some assumptions, but it was working well to our scientific goal, because this assumption, the main assumption that is doing MOOCs is that all the magnetic field is in the radial direction, and should be not true. Though the magnetic field has different topologies, so different shapes. So that's one of the things. So we have this synthetic library with is for Max models. Max models, you can use this model because is working well. They should work or might work better than other libraries on these regional temperatures in the K and M, 3,000 to 5,000 Kelvin, more or less. Okay. About that. So we create these things, and basically after we the first paper of the series, we just found that the best way to reproduce all the fundamental parameters, the stellar parameters of this young stellar object, we're using these 4 regions that we have here in figure. So these regions, you see, they are just in the K-band. We are using just this small part of the K-band. And this is just basically a combination. You are trying to look for lines that have a high response for one parameter, but not for the others. Just that would be an example. Just like there is a line here, for example, in the first rectangle on the first spot, and the upper one, you see the silicon and strontium different lines. So these lines respond in the opposite way, as a function of temperature. So those lines are a really good indicator of temperature. So ideally, you have this idea that, well, I have these lines, but in the real world, the lines, it's really hard to try to disentangle this different contribution of temperature, gravity, or so on. So you just try to do an average, right? An average, and trying to see which region is better and which line is better. Here in the second panel, you see another region where you have iron lines and also titanium lines. So these titanium lines and the previous sodium lines, they are responsive also to magnetic field. So this is really important in terms of magnetic field, the titanium and the sodium. And there is within our team in IGRINS teams where people working on magnetic fields. Just probably will be a paper soon on the magnetic fields in IGRINS Data. It will be really great. Stay tuned to that. And there was just like you have these different lines, you know that they respond to magnetic field. Let's use it, right? Absolutely. Let's use it and let's try to do it. So this region is basically there, just try to fix the magnetic field and somehow determine the magnetic field. And we have the other regions, the third and the fourth region, that they are just helping us to try to constrain the gravity also and the temperature. So in average, these 4 regions are I found that they are the best regions that we can use in the K-band to reproduce the observation. Cool. Or saying in the other way, the models are reproducing better these regions. Right. Yeah. Right. Fair enough. Fair enough. So it's basically just the MCMC, just really a summary to the people never heard about that. It's just we are comparing. True, we have this synthetic library, and you will have a lot of entries with different spectra. Each entry will be characterized for one temperature, gravity, magnetic field, and also the rotational velocity that I didn't mention, but it's also so this broadening. And the idea is you have an observation and you do a chi-square, just trying to see the difference and find the best fit, right? The best fit is that model that has the smaller difference between the observation and the model. Yes. But if we have this enormous grid, I don't remember how it was like a 2 million or something like that models. It will take a lot of amount of time. So we implement the MCMC, just is like doing the same thing, but in a smarter way, right?
A smarter way to do it.
Yeah. So it's just doing this thing, and we obtain that. And here, just in this figure, you see a black line, which is the observed spectrum, and you see a red line over the black. That is the best fit model that we found.
Yes.
So, and you see the residual in the small panel, you see some regions are better reproduced by the model, but not too much. But on the average is really
pretty good. It's pretty good.
I add in this MCMC temperature, gravity, magnetic field, rotational velocity, and also I just add a veiling factor or the veiling determination. So remember that the veiling is affecting the depth of the lines. So if I don't take into account this, I will have, for example, shallower lines. And in the models, which is an unveiled model, it will say, oh, it's a hotter or a cooler or higher or lower gravity. So it will be just an erroneous result. So basically, we obtain this. We have, for this work, I think it's around 65 stars from Upper Scorpion and Ophiuchus. Okay. And the beginning, we have all these things. We have just a visual inspection to see visually by eye to see if the fitting is correct or not. So we basically, sometime, for example, we found that if the star is rotating really fast, I mean really fast, higher than 50 kilometers per second, the rotational velocity, the projected rotational velocity, right? You won't see the lines. You see some lines, but it will be, the fitting will be really complicated to do that. And on the other hand, for example, if you have, it should not, but sometimes you have a giant or something that was just there. I don't know why, but it was just in your study. You will see that the lines are really shallow, and you reach the edge over your grid. And also we found some of binaries, the spectroscopic binaries that is not defined there, but you see it here and say, well, it's weird because you see the lines weird, and we just read of that. So at the end, we finished with 65. I believe 65. I don't remember the numbers, but it was around 65 stars. Which we classify in this way with different flags. Most of them were really good. And then with the first paper that we have more than 100 stars from Taurus, from Taurus Auriga star forming region, we create this in figure 2, we create this scale, this temperature scale. So it's something really useful, and there is a lot of people publish this kind of thing that you have in one axis. In the x-axis, you have the spectral type, and then you have the temperature in the way. So you can do a conversion between the spectral type into temperature really quickly. Right. And we have here the points are the scale that we created with the results of this survey, combining paper 1 and paper 3, which is Taurus Auriga, Ophiuchus, and Upper Scorpion YSOs, right? It should be stars within K0 and M5 spectral types. So we see that in the range on the x-axis. And here I can just point it out like two different things. The different lines, different colors are different scales that are already published, like a Hersey-Hindervan or Luhmann 2003. So different things with different methodologies and different approaches. So the first thing that we see is mostly the IGRINS temperature scale is just following the same shape, I would say. You see like something really steep, then like something wiggly, and just going up.
It goes back up. Yep.
So the thing is, from we can divide this part in 3. We divide it into the text in 3 parts. So from M0 to M3, we see that our results mainly agree with all the scales. Within the errors, we are mostly agree with all the scales.
Nice.
For late types or M4 and 5 stars, our result seems to be more close to this red line, which is Luhmann. So the scale is pretty similar to a Luhmann scale. But we see here in the other stream, in the hotter part, in the K stars, we see that we have a difference. Our result seems to be lower, so a little bit cooler, but it's following the same shape basically, but with an offset. So we really don't know why is that. Something that we are thinking is, as we were working on this, we were focusing more on the M stars. So we have more number of stars in the M part, and we have small stars in the K part. So we have just a couple of stars, a few stars. We have more, the most of the star M's. So that could be probably some of that. Another thing that could be correct also is that we found, or I found some parts that the spectra, you see here the literature spectral type, so somebody else determined the spectral type. And these spectral types, sometimes they have errors. So you see that there could be just erroneous classification, not all of them. Also, another important thing that we conclude from this series of work is it matters where you are obtaining the temperature from. So if you are obtaining the temperature from the optical wavelengths, it will be a little bit different than the infrared wavelengths. So there could be just a difference there, just because the methodology, just because the wavelength, and if you are using different, for example, models, line lengths, it will be just complicated. So probably that's we believe that the difference. But here an extra scale for the people that have a spectral type in this range, KM5, just wanted to use our scale, they are just welcome to do that, and we will obtain some results, right?
Cool. Yep, I'm with you.
So and we have these things. So we have all these parameters, and mostly the paper is just organized like a let's okay, we have temperature, gravity, and let's see what happened with these parameters, comparing within the different regions and comparing with different inside the region and with different regions. So it's like an internal and external comparison.
Yes.
So in this part, we can jump, I think is the figure, figure 3. So I will say this is really good. The figure 3 is, I will say that the result of this. We will see the HR diagram later, but I think this is the most important thing for me, at least for me.
One shot.
So we compare things, we compare temperatures. We don't see any difference in temperature actually between the different regions. So there was just mostly just following the spectral values because we had M stars. So then we try to look for the gravity. Okay. So here you see the different things, different colors. It's a little bit complicated to see it, so I will try to explain. So here is just the determination of gravity for the members of these different regions. In red is Ophiuchus, and this yellow or dot is Upper Scorpio. Then in green, that is Taurus from the previous work. TWA, this pink thing, and also you see field stars, right?
Yes.
So I had to mention this field star is from a previous work that we have more than 100 stars, 230 stars, field stars. So I just reanalyze now with this approach just to determine the parameters, the same parameters.
Right.
Modify a little bit the sequence is a little bit that, but it's just trying to see, because we wanted to compare how these things evolve with age, basically. So the field star will be an evolved counterpart for this young population. So the nice thing here, and it was something interesting to me, it was just trying to create a age ladder. So in that term, log G could be or might be a good proxy for age.
Yes.
So here you see more or less with some overlapping, but you see that Ophiuchus and Taurus, they are pretty similar in this distribution of gravity, right? Yes. This red and green thing is really similar. Right. And you see that those Taurus, TWA and Upper Scorpio objects, they are really similar between them. also. And that's right. And they are different between the other group. It's like there are two copies, right? It's the upper Scorpion and TWA. They are similar and really, really similar. And they come from the same distribution, we'll say. Taurus and Ophiuchus, they are really similar. So that makes a little bit of sense if we think that log G is an age proxy, because those ages are, I will say, Ophiuchus and Taurus should be around the same age, and we will leave it. And also the upper Scorpion and TWA, they're going to be more like a 10 million years, and they are pretty similar between them.
Okay.
But interesting thing is, you see, we see that there's difference here, and we are just saying that this difference could be because the age, right?
Right.
So with that in mind, we say we need a counterpart. So we just took these field stars that we already have observed with IGRINS, because we have, as I mentioned, we have hundreds of sources already observed. So I did the same approach, and we see the distribution is different. It's just different. And interesting thing is, you see like a double peak, and basically this double peak is around the K and M, just trying to reproducing the K and M peaks.
Okay.
More or less is really, really, really nice. So you see that and also it's just, this is just mentioning is just visually, right? But also with the statistics and different tests, with like a Kolmogorov-Smirnov test, that they are saying the same. So Ophiuchus and Tauro, they are statistically the same, coming from the same parent distribution, and is the same for the upper Scorpio and TWA. They are coming from the same parent distribution, and between them, you see that they are statistically different. So also, so just visually you see that one. At least I see that because I'm seeing these years and years. I hope all the people see the same as me. But also the status is saying that they are different. So this is just really, really interesting, because at the end we wanted to see this.
Okay.
But this was just one thing that say, well, we're saying in terms of gravity, they are different. What happened in temperature, they are not different. What happened about magnetic field, for example? They are different, they are not different. Well, the thing is, they are not different between regions. So it means that there is no something about the environment or DH, but say, well, we are not finding difference between the magnetic fields strength in a different region. What happens if we just try to divide our sample into like a small magnetic field or low magnetic field and high magnetic field?
Okay.
And see if these properties, we can just see the difference between that. And we found something interesting, that in some terms they are not different. So the two populations are the same, but in the interesting result, it was like the magnetic field, those objects that we classify like a low magnetic field. So they have lower gravity in average than the higher magnetic field. So this is interesting. This is interesting because if we think that the magnetic field is coming from a primordial way from the cloud, you see you have just a magnetic flux, and you have the star. As the star evolves, it contracts. So the gravity is just increasing, but also the magnetic flux will be increasing because it needs to be conserved. So that was more or less the idea. Our results are different a little bit, but we could be just some that we are just suggesting in that sense. So it was something really interesting about the magnetic field also of that. Another thing, it was we'll say about these figures, we see difference in gravity, and we are believing that this difference because an age gradient between the regions, but also the mass is just it plays an important role in the evolution of the stars.
Indeed.
So how we can just try to do that? So we have, you can jump out to figure, I think, I don't remember the number. Oh, we can just start with this. So here is a different representation of what we have. Actually, we have the HR diagram of this spectroscopy, HR diagram or kill diagram for the different regions. So it's really, really interesting. You see the circles are Ophiuchus, the stars are Upper Scorpion, Taurus are these crosses, and TWA are the squares. So TWA and Taurus from the paper number 1, and Ophiuchus and Upper Scorpion from this paper. And you see that we have a good number of young stars populating, and when you put it here, you'll see that they are populating different and similar spaces. I will explain that. So it was just the same as just playing in the other figure, like the squares and the star seems to be in the same region.
Yes.
Seems to be more constrained in gravity. But and you see that, and he said that like following these lines, this is the isochron, 10 megayear isochron, more or less. These isochrons are for Faden, which include the magnetic activity or the magnetic field. So these are magnetic evolutionary tracks for Faden 2016. Okay. And you see how this star seems to be mostly around the 10 megayears isochron, the squares and the stars. You have an outlier over here, but even more or less. But also you see the Ophiuchus and the Taurus, circles and crosses, that seems to populate very similar spaces, and it's around different things. It's just spread out all over this thing. So you see that within these evolutionary tracks, most of these objects are between 1 megayear and probably 10 megayears. So in the average, it will be around 2 or 3 megayears, which is not bad. But our goal was not determine age. So it was not that. So it was just trying to figure out if they are different. And it seems to be that are different, and it's really, really interesting for us.
Absolutely. Very cool.
We just then, as I was mentioning, we have another thing. We have this spectra, and just trying just to determine more things. So the thing is, we just gather information, photometry. Basically, we gather 2 mass, J, H, and K. Okay. And also WISE photometry to do the SED from all these things, all the available things. So the idea from this is we want to measure the alpha index, which is just a classification index, because I mean the class 2 and class 3. This alpha is just the slope in the infrared SED. So basically, and it's just saying that if you have a different slope, you will have an infrared axis or not, due to the presence of a disk. And with this idea that the presence of a disk, it will say that it's not as a ball as in the other counterpart, right? Because you have a disk, so the first stages of the star. Yes. We have that. We have this thing. We have all this catalog of parameters. So let's see what happened with this classification. So we gather the photometry from literature, and you need to do a process of constrain the SED and then use the redden this SED, because they're just extinction, visual extinction, convert extinction to K extinction. And for that, we use another code called Massage that was written by a colleague here in the UNAM, here in the same institute. We're just basically using, in that case, for that code, you introduce the temperature of the object, and also you you use Gaia photometry and also 2 mass photometry. So basically you have these different colors, construct different colors with this photometry, and based on the colors, intrinsic colors or lumen, just produce like just trying to modify the extinction until you have a best fit between this observation and this theoretical approach. So we have the extinction, we have the SED with the RENEDA, and we can just obtain this alpha parameter, which is within the classification, or is related with the classification of the star. So now we have a bunch of stars with parameters. We are just trying to compare. We see these things in gravity.
Yes.
We see that they're similar in temperature, they are similar in magnetic field. We see this difference in magnetic field as some hints of things happening, physics happening there. But now we have the classification of these samples. So we classify that in different regions with the different alphas, and then we use a classification and try to see if these indices is related with some of the parameters.
Okay.
Right. So just to try to pull the same information back from the other perspective, trying to say if the evolution of the study is affecting more one parameter or not, or if we can just see it from some parameters. So we found for temperature, for example, in class 2 and class 3, we found basically that they are really similar. So there's no different, and it's something expected because you don't expect anything different between the young and more evolved stars. So you're just making that we have could be just because we are observing these M stars. So it will be M star, we will have the same or more or less the same distribution in temperature.
Cool.
So in log G, we found that we found a difference with low significance, but we found a difference between these stars. Class 2 have a lower gravity in average when we just put that class 2, and class 3 had a little bit higher gravity, log G and average. So it makes sense a little bit because you come from lower gravities to higher gravities as you evolve. So it's more or less that was the idea that we had. It's just something expected, but I said some low significance because our error bars that are a little bit higher. Another thing is also for this class 2 and class 3, something that is interesting, but also is we need to, it's just there. We need to check more in detail is about the rotational velocity. We found that class 2 rotates low, they are slowly rotating than class 3. And this is just a hint about the disk, this locking scenario, that you have this interaction between the star and the disk, and it's just perturbing the rotation of the star.
Yeah.
So it's really interesting that. So here the final thing that we do about all these things, about all this paper is just in figure the previous one. It was just like a try to separate our results in different temperature bands. Just to say they are cool stars, they are mid or warm star, and then hot star. So that in figure, I think in figure 7, we just try to compare that, just try to see if the temperature here, the temperature is we use it like a proxy for the mass.
Yes, right.
Proxy for the age, we see that they are different between the different regions. There are some regions that are similar between them and different between them. We try to see if the mass is playing an important role or not, or at least in our determination. I know you see these things are really interesting. The first panel in the left is comparing the gravity. You see how the gravity is increasing. It's really nice increasing to what the different things. And you can use in the x-axis, you can see the different regions, and you can think like a age. Right. Something about age. No? You see like Ophiuchus and Taurus, they are pretty similar in the terms of gravity. In the I think this is low and mid temperature range. We divided the temperature range, and in the hot range, the temperature seems that is more step this. Right. It's really some part something. It has to say that the beans has a low number of stars. That's the reason that it's just going down. But you see, in the general behavior is like you are coming from lower values to higher values. So but you don't see a different or a high difference between the different figures, the different colors, right? Circles, squares, and triangles. circle and square are really similar, but triangle is a little bit different because they are higher temperature. But
Yes.
we need to explore more that. It's really, really interesting.
Okay.
In terms of rotational velocity, you see, which is something interesting, like is going up and then going down. The rotational velocities, at least I see that in the squares and circles.
Yeah.
The Ophiuchus seems to be a rotator, a little bit more, rotating a little bit more Taurus, and then just going down onto the field stars. And that just makes sense because the all stars should be as slow rotators, at least the kind of stars like our main sequence stars that in average that the more or less the
right. You're getting some sort of a braking, magnetic braking mechanism going here.
Yeah, it's just the evolving, the rotational evolution of this that is just normal. That, and you see the final panel. We just trying to see the veiling. Just try to see if, for example, this veiling is related with the temperature of the star. And you see that there is no such a thing, right? It's really flat. It's not, this temperature is not something that is affecting the veiling. It seems to be a different thing. So that's something about the results that we have with mass, or we say this proxy on mass, really nice in the different regions. Okay. So and I think that basically the result that we have with this work, we're obtaining different values of the different things. Basically, we extended the work that we did in the paper one, and we extend also to things that I did previously as the field stars in the appendix. That there is a figure which is really nice and interesting in that appendix.
Let's take a look at that figure.
Yeah, the thing is that this is from a paper for 2019, which we determined in that paper. We determined the temperature using a technique,
line depth.
Using line depth lines, just a couple of pair of lines in the H-band. So that's another thing. It was in the H. We just trying to explore. It was my first approach to this data. We said always you approach from the easy part, and you go
generally, yes.
And here they say, well, we have the spectra, we have the tool, we have the codes, everything just is running. In this case, for example, we omit the parameter of the veiling because you don't expect any veiling in this kind of star. So we are just determining the same, but not using the veiling. There's an interesting thing. We are comparing this work with MCMC determination in the X axis and the line depth temperature that we determined in 2019. Got it. You see a good agreement within the error is a high error. You wanted 300 Kelvin. Okay. But you see something that is just something around some other more spread and so on. And the nice thing is well, in that work in 2019, I do a lot of assumptions. One of the assumptions was I just fixed the gravity for doing this job. So I was say, well, they are just K and M stars, so the gravity should be around this value, 0.5. Let's fix it, and it's be let's determine the temperature, just the temperature. And you see that in the color bar that there's the gravity, So going from the red lower to the blue higher. So the value that we fixed in that paper, it was around the 4.5, was around like a yellow or something like that. Okay. You see that most of these yellow objects are around the 1-to-1 line. Yeah. So we are determining that. We see that this spread is a function of the assumption that I made in 2019, but also we recovered good determination of temperature. Yeah. And the nice thing about that paper that I mentioned here and I mentioned in that paper is the line depth temperature is really easy to do it, and is working well also in the young stellar objects. So you can just go there and see the star. I just say to the students and all the people that I'm talking about is, I see this region in the H-band and I know if it's a hot or not a star. So I know mostly the temperature just by eye, because I see hundreds of stars. And it's really nice. You can obtain a good value of temperature within this range because the lines are not, they are just working between 3,000, 3,100 to 4,300, something like that. That's the reason you see this flat part.
Flat out, yeah, up here. Right.
Line depth temperature, there not have more resolution, or they cannot be determined these high temperatures.
Right.
It's really good. So we recovered this part in the IGRINS. I was in the survey as an instrument. We compile this thing. We start with the field stars, then the jump stars, and then at the end we combine everything, and we see that we're obtaining really good results and really expected results, and that we can just obtain more and more from the data. I think that's all of what I wanted to say or had to say about this. I just invite all the people that want to read it and have some doubts, just write me an email or something. So I'd be happy to talk with the people and trying to do. And also I just repeat myself that the IGRINS team UT just published this RISA, RRISA catalog with all the observation in raw and also on the reduced one. If somebody else wants have some interesting object and see if we have the spectrum, right?
Yeah. Okay. Very cool. Very cool. Ricardo, thank you so much for walking us through this very awesome article. It's great.
Thank you.
So you touched on it a little bit as you went through, and let me push on it a little bit. So let me ask, where do you think we go over the next 2 to 5 years on this topic? This is paper 3 in this series. Will there be a paper 4? Will there be a paper 5? Are there other instruments that can be useful for this? Newer instruments, let's say JWST, maybe Roman coming up. Is there theoretical work that could be done to produce better models? So where do you think we go over the next couple of years on this topic?
Yeah, I think there is a lot of room to do here. One of the things that I don't mention, but because it's really complicated to do it fast, but it is something is the concept. You see that we are using synthetic spectra. So the spectra are not well defined in this temperature. Well defined, a little bit defined, or you can useful. They are useful, but if you go down to late M or L or T stars, there's more complication there. So there are groups of people working on that. So some that I will say in the future, from the theoretical counterpart, from the theoretical point of view, that should be something the theorists work on this and trying to improve the models of cool stars. So we need to give them as observational astronomer, just try to provide the observation and try to do that. In this instrument is really good, and there is another one. So from the observational point of view, the IGRINS team that we're working on another instrument that it will be really, really good. I don't remember. I think it's GMT NIRS for this Giant Magellan Telescope.
Oh yeah. Okay.
So this GMT NIRS, as I understand, probably could be wrong, but this instrument will have IGRINS had 2 bands, and you have observation of 2 bands, H and K. So this instrument, this near future instrument, will have 5 bands to observe. Nice. So it's at J, H, K, L, M.
Nice.
So the thing is that now we have, and there is really interesting because this is 45,000 resolution. So it's high resolution for these things. So I saw some signs because I was just also involved in the observation with the IGRINS for other people, said different approaches with these cool star atmosphere, just working towards the planetary atmosphere, right? Just try to characterize that. Because we are just in the limit with the IGRINS that we can just have like an L or T star, but in the future, like a James W telescope, another future instrument will go down to not to stars, but to planets. I think that's the future in that.
Get the whole solar system
going. Really nice because this spectra from I don't remember the instrument. I think SPEX or something like that. Solution in the infrared and for this LT star. So you see just small points, and you put the IGRINS data, which I had to say it was really hard to obtain, and also it was lower signal to noise to have it. But you see a lot of feature. It was really beautiful spectrum.
Nice.
And also when I was talking with my colleagues in UT, and some told me that it's really nice, but also it's really, I don't know, it's really scary, because all this information, all these lines, we need to know what's from that.
Yeah,
right?
exactly.
We
That would
need
be
to
useful.
improve our models to
Respect.
understand what's that. So I think we need to, we have at this point, I think the instruments are just ahead a little bit of the theoretic part. So
Yep.
we need that the theoretic part started to do models and improve the models, and people are working on that, but
Cool.
I think we need more and more of that.
Cool. Very nice. Very nice. Well, I really look forward to this topic moving forward over the next couple of years with some new models, some new observations. It'll be really great. Very cool.
Yes.
Ricardo, thank you so much once again.
Thank you, Frank. I really appreciate this time.
Thank you. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.